natural convection. So we started to see some things last class. We saw a video, and what we saw is a natural convection is, from our point of view of heat transfer, is the transport of heat due to the combined the combined effects of advection and conduction through a boundary layer. This so far is the same that all the other types of convection we have seen. The important difference now is that the velocity is not externally imposed. So we are not able to calculate a Reynolds number easily because we don't know what the velocity is. There is a velocity and we could calculate a Reynolds number. The problem is we don't know what that velocity is, right? And that subtle difference makes a world of difference in practice. So most of what we are going to see resembles very much what we have seen so far, except that now we don't have a Reynolds number anymore. We're going to have something else that does not require us to have a velocity, a knowledge of a velocity to start. So as we mentioned last time, we're going to look at things much the same as we saw before in flat plates, in spheres, in cylinders. We're going to see convection in natural convection in outer flows. We're going to see natural convection in internal flows. And we're going to see something new that is natural convection in enclosures, in which we have recirculating flows. And in the end, we're going to see what happens when we combine natural and forced convection. So let's see a little bit about the origin of natural convection. So let's say we have a fluid that is trapped between two horizontal plates. And this, although this is an idealization, much like similar to this is what happens in the atmosphere or in water in many occasions. So we have two possibilities. If this pinkish orange one here is the fluid and this gray are the plates, we have two possibilities: that the top is colder than the bottom, or that the top is hotter than the bottom. Let's see the first case, that the top is colder than the bottom. So let's assume that fluids expand with heat. It's not always the case. I'm going to tell you some, but almost always is the case. So if the top is colder, that means it didn't expand, it compresses, so the density is, let's start with the one here on the right, that the top is hotter. So if the top is hotter, the fluid expands, the density is lower, and because of buoyancy, wants to stay up. So in this case, in the right, the high temperatures at the top and the colder temperatures at the bottom, we have low densities at the top floating on top of higher densities at the bottom. And this fluid is stable. This is the type of problem that happens, for example, trapping smog in Los Angeles. You have a stable temperature gradient that nothing moves there. So if you have smog, that's where it stays. And this is, for example, what happens at night. The ground is cold, and the hot air stays on top, and the colder air stays close to the bottom. Now let's look at the other case, the case in which the top is colder than the bottom. So now we have at the bottom the hotter fluid that we assume that if it is hotter has lower density, and if it has lower density will want to go up by buoyancy. And as it goes up by buoyancy, it starts to create a flow, right? And it goes up, and if some of the fluid goes up, they call the fluid then is going to come down with higher density, and you can have these recirculating type of flows. And many things happen in many different shapes now. This is the case, for example, of atmosphere during the day. The lower atmosphere that was in a stable condition at night, when the sun hits the ground and warms up the ground, where this warmer, the ground warms up the air right on top of the ground, and this tries to rise. And this generates more turbulence during the day than during the night. So, of course, the cases we're going to be interested in are these type of cases in which we have an unstable situation that creates a motion of fluid at a velocity which we don't know what it is, but that velocity causes advection that transports heat. So we were talking about the thermal expansion coefficient. So we're going to call it in this class beta. That is the derivative of density with temperature at constant pressure, and is divided by the density. So it's essentially something like a % volumetric increase per unit of temperature. Almost always, this thermal expansion coefficient is positive, right? Like density decreases. That's why we have a negative sign here, right? As we increase temperature, density decreases, which would be a negative derivative. That's why we have a negative sign, but beta ends up being positive. So it almost always is positive. Let me tell you a well-known example in which beta is negative. Is water between 0 and 4 degrees C. Is liquid, but for those reasons of the molecular structure of water, between 0 and 4 degrees, as you increase the temperature, water also increases the density, doesn't decrease the density. Beyond 4 degrees, water behaves like a normal fluid. So here we have the expansion coefficient. This definition applies to any fluid. Now, for the particular case of gases, we can use an ideal gas as a good approximation. And we, here this equal sign is in the wrong place here. This equal sign should have been up here. But when we apply the ideal gas law to this definition, we come up that beta is 1 over T, 1 over temperature, of course, in Kelvin. So it is interesting. So for gases, beta is trivial. For liquids, no, it's not trivial and needs to be tabulated. So these are the very, very basics. So let's start moving up the chain of interesting problems. And the first thing we're gonna see is the case of vertical plates. So vertical plates are pretty much the same as what we have seen for when we studied boundary layers. We studied the flat plate, and gravity didn't matter then, right? And we said if the plate is horizontal, we have a flow imposed on it at a velocity u infinity that would come from left to right, right? Those type of things. Now we're gonna do the same, but we're gonna consider a vertical plate for the reason that the velocities due to buoyancy go in the vertical direction. So this plate we have here is very much the same plate as we were looking before, but it's vertical, so buoyancy can create flows parallel to the plate. externally, there is no velocity implied. So when we go really far away from the plate, velocity, what would be the u infinity, that's 0. And on the plate, we also have a velocity that is 0. Now, somewhere between the plate and infinity, there is a velocity that is not 0. And this is the type, the shape of the velocity profile. So we have 0 velocity in contact with the plate. As we get farther from the plate, velocity increases, much the same as every other boundary layer we have seen so far. Except now it gets interesting. Now, velocity, we know that when we go back to infinity, velocity is 0 again, because it's what we call a quiescent environment, quiescent fluid. So it only moves when it's near the vertical plate. So after it has reached some maximum velocity, starts to come down again until it goes back to 0. So this boundary layer is different than the boundary layers we have seen before. So let's make a comparison here. Let's see if this turns on. Here we go. Oops. Okay. So, oops. Let's see if this Bluetooth works. Well, things seem to be rebelling. Okay, too bad. Oh, here, finally. Okay, so in a vertical plate now, that should be straight. Let's make it better. Okay, so let's let's try to make a vertical plate again. So in a vertical plate with convection, we had that our velocity profile was, if this is the y-axis, and we say vertically we have a velocity profile was 0 on the wall, starts to increase, gets to a maximum, and then decreases. And this is our boundary. Now, the boundary layers we saw before were quite different, because we would see something that, let's make a new plate so we don't get confused. And this is you, and we saw something like, well, it doesn't want to go. So we saw velocities that would go to u infinity, right? They don't go back to zero, right? And that's the main difference what we have seen before. Okay, so this is for the case of fluid flow, and we're going to have a thickness of the boundary layer from the point of view of the temperature. So let's say the same as we said before, that the temperature, that the plate is hotter than the fluid. And in this case, it matters because for a boundary layer that is going up, it can only happen if the plate is hotter than the fluid, because in a gas can only happen if the plate is hotter than the fluid, and for water above 4 degrees can only happen if the plate is hotter than the fluid. So we would have this boundary layer, and the temperature that is high against the plate comes down to the towards infinity. We have the temperature T infinity of the quiescent fluid. In that aspect, this boundary layer doesn't have exactly the same shape, but looks very much similar to the boundary layers we know from forced convection, right? High on the plate and goes to a constant value. And this thickness would be the thickness of the thermal boundary layer. Now, this is a graph of temperatures, graph of velocities, viscous boundary layer here, thermal boundary layer in here. Now, let's not worry right now about what this crazy axis we have here. Let's say that this axis here is, what matters is this y, that is the distance away from the wall. And this other vertical axis here is proportional to velocity. Let's not worry about other things because it's just a normalization. And what these graphs show us here is what the profile of velocities is going to be. That is very much this little drawing we have here. And why do we have many different curves? We have them for different values of Prandtl, from 0.01, that is molten metals, to 1000, that is oils, right? And what we have is how the, in all cases, we see velocity increase, reach a maximum, and then go back down towards zero again. And this graph here on the right that has similarly crazy axis again, the horizontal axis, let's only pay attention to y. And the vertical axis is normalized temperature. This is normalized the way we have done it many times before. T minus T infinity divided T surface minus T infinity. And we see curves similar to this one here. Now, because we're doing T minus T infinity, this is the reason these curves go to zero. And we get to see, again, that as we decrease the Prandtl number, right, as the fluid is more and more conductive, the thermal boundary layer keeps expanding. So now, what is interesting of these curves, and this, if you remember, Prandtl had a student that was Blasius. Blasius solved the equation of the isothermal boundary layer and decided to quit for good. I don't even know who solved the equation for the vertical plate, which is a hydrodynamic boundary layer coupled with the heat transfer. But they did it. And what we see here in these crazy numbers is that what they found is that the profile, this velocity profile, is the same at every point in the boundary layer. It's just the same. And what changes is like the magnitude of how thick the boundary layer is and how big this velocity is. That's why we have X that says how this parameter is going to vary with length. And same here, we have x. And then we have this other term here. This GRX, GR is the Grashof number. Please don't call it GR, it's the Grashof number. And X means it's the Grashof number based on distance X from the leading edge of the plate. Clearly, because this is Grashof of X, this is a local value, whatever those are, local. I want to tell you more. I will not do this derivation, which the book doesn't have either, but you can do some back of the envelope thing. And you come up that if you do some sort of a force balance of buoyancy against viscous friction for this boundary layer, you're going to come up with a number such as this one here. This a group of parameters such as this one here. This group of parameters is what is defined as the Grashof number. In this case, we have length, so Grashof of length. Grashof behaves very much like a Reynolds number. So in a Reynolds number, you have a relationship between inertial forces and viscosity, right? And you assess this ratio because you know the velocity. In this case, you don't know the velocity, but if you more or less guess the velocity based on this force balance in the boundary layer, and you plug that guessed velocity based on temperatures and thermal expansion coefficient, then you end up with this Grashof number. And that's why it appears here, the same way we used to have the Reynolds number appearing all the time. Now we're going to have the Grashof number. There is another number, which we're going to see in the next slide, that is called the Rayleigh number, that is similar to the Peclet number. But and Peclet was a ratio of advection to conduction, right? This is quite somewhat similar concept. So to read these graphs here, we need to know the Grashof number that is based on the gravity, which we know. It depends on the thermal expansion, which we know based on the fluid. The surface temperature of the plate, we're assuming in this case, is a laminar plate of a known surface temperature of the fluid, and nu is the kinematic viscosity of the fluid. And here we have how tall our plate is. Taller plates have higher Grashof numbers, right? And it would make sense because a taller plate would have a lot more force due to buoyancy. Some of you must have seen, must have been exposed to formulas for chimney to calculate the draft of a chimney. And the taller the chimney, the bigger the force. This is the same concept. The taller the plate, the bigger the force is going to be. Here we have Grashof. And look at this. If we want to calculate now a local Nusselt number in a plate, we say no problem. We have these formulas that some poor soul did, and by now, other than the force balance that I would take credit as my own, all the rest of the fine math was somebody else's suffering. We get this expression that says Grashof, and here the derivative of temperature against eta, that is essentially this derivative here. And when you do all these operations, you end up with Grashof to the 1/4, right, over 4 times this function g. I'll draw your attention to two things here. This Nusselt number, the Nusselt number for natural convection in laminar flow has a Grashof to the 1/4. Let's keep this in mind, because much like when we had the Reynolds that was coming Reynolds to the 1/2, now we're going to have this Grashof to the 1/4 appearing other times. And then g of Prandtl. And this function g is explained here. And what do we see? That when Prandtl tends to 0, as it would be the case of a molten metal, when Prandtl tends to 0, these two parts would go away, and we would have Prandtl to the 1/2, similar to what we have seen before for molten metals. Now, if Prandtl is very big, such as the case of oil, this term here is what is going to dominate, and we're going to, and is Prandtl to the 1/4 that gets abstracted to this. And so it's for the case of oil, this function G tends to be something along the lines of Prandtl to the sorry, instead of being 1/2, now it's going to be Prandtl to the 1/4 for the case of oils. Grasov to the 1/4, Prandtl to the 1/4. Typically, these two appear combined in the correlations we're going to see. So here what we just saw was how to calculate a local Nusselt for a vertical plate in laminar flow. And this is, and all this tabulation is based on this Krasov number that for the case of air, water, and oil is going to have here a factor of more or less Prandtl to the 1/4. For the case of turbulent flow, we need what is being done empirically, and the correlations have the shape that we see here. Nusselt, and in this case, is not a local, is an average, is a constant C that is empirical times Rayleigh to the n. Rayleigh is defined as a Grasov times Prandtl. The same way we would say the Peclet number was Reynolds times Prandtl, the Rayleigh number is Grasov times Prandtl. So if Rayleigh is Grasov times Prandtl, in our previous case, in which we had Grasov to the 1/4 times Prandtl to the 1/4, was the same as saying that Nusselt is Rayleigh to the 1/4. And this is what they say in these empirical correlations. When we have laminar flow, we're going to do correlations with Rayleigh, and the exponent will be to the 1/4. In the case of turbulent, the empirical evidence is that the exponent here is not 1/4, but 1/3. And this, let's see. And this has an interesting consequence, because if in turbulent flow we have Rayleigh to the 1/3, we'll see the formula for Rayleigh, and we see that has length to the cube. So in the turbulent flow, Rayleigh to the 1/3 is proportional just to length. And we have H L over K equals to something proportional to L. This means that the convection coefficient H is now independent of the plate length. And this is very interesting, because if the coefficient H is independent of the plate length, means that it's constant, and it also means that the average and the local convection values, or average and local Nusselt numbers, are the same, right? And sorry, the local and average convection H convection values are going to be the same, not the Nusselt. So the Nusselt is proportional to L, but so convection coefficient is constant, and the average will then be constant. This is an interesting finding. How do we know if we're in laminar or we're in turbulent? Our first reaction would be to check the Reynolds number. but good luck with it, because we don't have a velocity to put in the Reynolds number. So we saw that the more or less equivalent of Reynolds is the Grashof number, and Grashof times Prandtl is the Rayleigh number that they tend to come together, right? Grashof and Reynolds. So the criterion for turbulence is based on the Rayleigh number. And we're gonna say that a plate is laminar when the Rayleigh number is less than 10 to the 9. And when the Rayleigh number is more than 10 to the 9, it's going to be turbulent. So now we know, same as before, our first step used to be check the Reynolds number to know if it is turbulent or laminar or whatever it is. And now our first step is going to be check the Rayleigh number to see if it is turbulent or laminar. If the Rayleigh number is more than 10 to the 9, here we have correlations C times Rayleigh to the n. And I'm going to be showing you correlations in the next slide. And if the Rayleigh number is less than 10 to the 9, here we have, for the case of local Nusselt and local age, we have another correlation that comes from quite fundamental treatment. So these correlations I'm showing you here, these are empirical. So let's say you want the average Nusselt for a vertical plate that is at constant temperature. And here you get to see for high Rayleigh numbers, and you see that Rayleigh number can be many orders of magnitude, right? Rayleigh number to the 1/4, as we had already seen. And here we have some business with the Prandtl number that is to accommodate to a broad range of Prandtl numbers. You see this constant value here? This constant is just accounting for the fact that when there is the Rayleigh number is small, that means here we have the expression of Rayleigh number. When Rayleigh number is small, means either there is no gravity, there is no expansion, or there is no temperature difference. But in any case, that means the flow is very slow. And the flow, if the flow is very slow, advection is not so important, and conduction starts to play a role. And that's why we have this 0.68 that accounts for us approaching to a conduction problem. If you want an average Nusselt that accounts for the laminar beginning and the turbulent downstream, you have this one that accounts for all cases, including turbulent flows. Let me tell you something interesting as I was discussing this. We mentioned that convection in this course is driven by differences in buoyancy because of the expansion of the fluid, right? When you're making semiconductors, you have this molten bath of silicon, and you might have some dopants there, or some impurities. And as the fluid is recirculating because of natural convection, those impurities get distributed and can be a problem making semiconductors. Do you want to know one of the first experiments that was made in Skylab? People were melting silicon in space. And now gravity, instead of being 9.81, was something, is never exactly zero, but was nearly zero. Is what they call microgravity, right? You reduce things by 6 orders of magnitude. And all of a sudden, the Rayleigh number pretty much disappears. And you don't have the buoyancy to drive this natural convection. Even if you have expansion, it doesn't matter anymore, because the fluid that is less dense doesn't have a reason to float to the top, because there is no gravity causing this, the difference in density to make the heavy sink and the light float. Isn't that interesting? Yeah, I think is a pretty cool thing. So this Rayleigh number captures lots of depth of the problem. So let's say instead of a wall, we have a cylinder, like a chimney, as I've been asking for years about chimneys, you might have seen in the exams. And guess what? If the boundary layer is thin, right, the boundary layer due to the natural convection due to the advection moving up, right? If the boundary layer is thin, then it would see the cylinder the same way as flat, the same way we think the Earth is flat, right? If I look around, looks pretty flat to me, right? I know the Earth is not flat, but from my height, looks pretty flat. The same for the boundary layer. If the boundary layer is thin, it will believe that the cylinder is in reality a wall. So for a chimney or a vertical cylinder that there are so many cases, I'm just going to use the correlations for a wall. Now, how do I know if the boundary layer is thin or not? So the criteria is thin compared to the diameter, right? The diameter has to be bigger than something. And here's the ratio. The diameter has to be 35 over Grashof of length to the 1/4, right? And with this criterion, we just can discriminate if we have something that we can consider as just a wall and we're happy, or not. And if the answer is not, the book is not giving us a formula, and we would need to go to the scientific literature and find something. So our favorite, like chimneys. So let's say that we want to calculate the convection coefficient H for a chimney in still air. Let's say that the chimney is at 44 degrees C and it's surrounded by air at 20 degrees C. Let's say that the chimney is 10 meters in height and 1 meter in diameter. So this definitely is not to scale. X is 0 at the base and moves up, because the leading edge for natural convection is what is at the bottom in this case. The fluid not always moves up. For example, right now that is fairly chilly out there. When the wind hits my window, when the air hits my window, when it's chilly out there, when the inside air hits my window, that air inside that hits the window goes down, it falls, it doesn't go up. Okay, so let's take a look at this example of the cylinder. Here we go. Step number 1. We, same as before, we need to check for Rayleigh. In the past, we used to check for Reynolds, but we have no idea what Reynolds is because we don't have a velocity. So we check for Rayleigh. And at what temperature do we calculate the properties of the fluid? Do we calculate it at the temperature of the wall, that is 44 degrees C? Do we calculate it at the temperature of the free flow? And the temperatures we're going to pick are the film temperatures, right? That is the average between surface and T-infinity. This is what we call the film temperature. And we have discussed long ago when we first started to discuss convection. So the average between 44 and 10 is 300 Kelvin. Oh, how conveniently chosen. So at 300 Kelvin, the thermal expansion coefficient, the volumetric expansion coefficient, is 1 over T, that is 0.0033, and I keep going, 1 over Kelvin. This is cool. In gases, beta is very easy. For the case of liquids, no. Liquids, we need to find it tabulated, for example, in the book. And the book, if you look at the book for water, it has, it shows you, let's see. Look, in this case, we have a page of the book that gives us temperature, right? And the expansion coefficient for the case of water. Right? And here it shows how the thermal expansion, the density goes down with temperature, right? But the maximum is not at 0, it's around 4 degrees. And then on the other hand, you have ice. So, oh, no, I didn't want to go there. I wanted to go here. So we got beta, we get the kinematic viscosity because we were just given the Prandtl number and thermal diffusivity. So alpha times Prandtl will give us kinematic viscosity. And with this, we can calculate the Rayleigh number. So that is this expression that you cannot possibly memorize, but it is in the formula sheet that I uploaded. And it is in the book or in the slides all over the place. So I calculate this and I get a value of 3 times 10 to the 12. It's huge. It's huge. What the limit, our critical Rayleigh was 10 to the 9. This is definitely turbulent, right? It's a 10-meter chimney and it's quite turbulent. So can I use my correlations for a wall? If the answer is no, then I don't know what to do. But if I can use my correlations for a wall, then I'm a happy guy. I'll be calculating a cylindrical chimney, assuming it is just a flat wall. And D over L is 0.1 and 35 over Grashof to the 1/4. That was the condition. This criterion here, I applied this criterion, and it gives me 0.024. So the diameter is a lot bigger than the critical value for using it. So yes, because the diameter is so big, and the boundary compared to the boundary layer, I can assume that the chimney is a flat plate, and I'm going to use those correlations. So I'm going to use the correlation that is kind of more universal. Where do I have it? Okay, here. This is a correlation that is for the entire range, right? That includes laminar and turbulent, and depends on Rayleigh number and Prandtl. Both things I already calculated, so we're happy. I'm happy with that. And I calculate then a Nusselt number of almost 1600. And this was it. Look, when we see this equation full of exponents 9/16, it raised to the 827, we think this is crazy. This is just empirical. These are not numbers that come from anything exact. And if you think it's a pain to plug and chug into this equation, just think how lucky you are that you're not the person who had to write this equation by measuring an infinite number of flat walls, right? Until they could get a more or less reasonable correlation. So we get more or less 1600, and then we unpack it to get H, the convection coefficient H, and we get 4.2 watts per meter square Kelvin. Do you remember? If we didn't go through any of this, I would have called it 10. I never explained you why, I just said 10 works. And because I couldn't explain why, if I didn't even say the system, I said natural convection in gases, more or less 10. Now we get serious about it, and we got 4.2. I'd say we're not too bad. I think we're not too bad. So so we can do some ballpark estimate of the thickness of the boundary layer using the same things you used in quiz 3, right? And we get that the boundary layer would have a thickness of the order of 6 millimeters in a 1 meter diameter, definitely thin, right? Let's calculate other interesting thing. When does turbulence start? We know at the leading edge, at the very bottom of the chimney, natural convection is laminar. Just same as in a flat plate in forced convection, because at the beginning, it's always laminar. It gets turbulence downstream when the Reynolds number gets big, or in this case of natural convection, the Rayleigh number gets big. So let's say Rayleigh number of X, right, would be when, at what X does it become, does it reach the critical Rayleigh number? So I solve for X, right, which is this line here, and it tells me that the turbulence in the chimney begins at 68.5 centimeters from the bottom. So I have a 10-meter tall chimney, and in a distance of this order here, it becomes turbulent, and then it never lets go. And something interesting, the thickness of that boundary layer and the convection coefficient of that boundary layer, as it goes up the chimney, doesn't change anymore, gets fixed, right? That's one of the results we had seen. And this is particular for natural convection in turbulent regime. In natural convection, in turbulence, the convection coefficient becomes constant and doesn't decrease as we move farther downstream. All right, I think this is an excellent point to stop. I'm gonna take 10 minutes. And for those of you who wish to participate in the office hours, I'll see you then at 2 p.m. Thank you very much.